We've all been there, right? We write our code in a language that makes sense to us, but our computers, they only get ones and zeros. So how in the world do we bridge that gap? Well, today we're going to take that exact journey right into the heart of the compiler.
For so many of us, hitting compile is like magic. You shove your precious source code into this mysterious black box, and hopefully a working program pops out the other side. But what is actually going on inside that box? That's the magic trick we're going to unpack today.
Okay, let's zoom out for a second and look at the big picture. And whoa, it's not just one step, is it? Your code goes through a preprocessor, then our compiler, an assembler, a linker, and a loader before it can even think about running. Now that is a lot to chew on. So today, we're going to focus on the real star of the show, the compiler itself.
So here's our plan. First, we'll lay out our code factory roadmap. Then we'll take a tour of the two main departments, the front end and the back end. After that, we'll give a shout out to some unsung heroes of the process. And finally, we'll tie it all together and see why any of this actually matters to you.
Honestly, the best way to picture what a compiler does is to think of it as a highly organized factory. It takes your source code as the raw material and sends it down this super organized assembly line, where each step transforms it, getting it closer and closer to the final product.
And here it is. This is our factory map. We're going to keep coming back to this, so get familiar with it. Every single box you see is like a station on that assembly line. It takes what the last station made, does its own special thing to it, and then passes it on down the line.
Now this factory is basically split into two big sections. You've got the front end, which is all about analysis. Its job is to understand what you wrote. It speaks your language, whether that's C++ or Java. Then there's the back end, which is all about synthesis. Its job is to actually build the thing the machine can run. It speaks the machine's language. And you know, this split is actually genius. It means you can have one front end for, say, C++ and connect it to a bunch of different back ends to create programs for different computers. Super flexible.
All right, let's start our tour. First stop, the front end. Think of this part of the factory as the quality control team for the blueprint, which is your code. Before a single thing gets built, they have to make sure the plan is solid, that it makes sense, and that all the instructions are correct.
Inside the front end, there are three main stations. The first is lexical analysis. This is like someone reading your blueprint and just identifying all the individual words and symbols. The second is syntax analysis, which is like checking the grammar. Do these words form a valid sentence according to the rules? And the third, semantic analysis, is the big one. Does the sentence actually mean something sensible? Okay, let's use a real example. Look at this line of code. The very first thing that happens is the lexical analyzer scans it and breaks it down into these things called tokens. You can just think of them as the basic building blocks, the words of the code. Every variable, every plus sign, every number gets its own little token. And those ID tokens, they're just placeholders, pointing to a list where we're keeping track of our variable names.
Okay, so after we have our tokens, the syntax analyzer steps in. It takes that stream of tokens and tries to build a sentence out of them, like a grammar tree. If it works, great, your syntax is correct. Then the semantic analyzer comes along and checks for logic. It looks at that tree and says, okay, I see rate is a decimal number, but 60 is a whole number. You can't multiply those directly, so it makes a note. We're going to have to convert that 60 into 60.0 before we do anything else. It's catching those little gotchas for us.
All right, the blueprint has been checked, double-checked, and stamped for approval. Now we can head over to the other side of the factory, the back end. This is where the real construction begins. We're about to turn that abstract plan into an actual thing the computer can run.
And just like the front end, the back end has three big stations. First, it creates something called intermediate code. Think of it as a generic, simplified set of instructions. Next, and this is a really cool part, it sends that code to an optimizer to see if it can be made faster or more efficient. And finally, the code generator takes that polished code and translates it into the specific language of the computer it's going to run on.
So here's what that intermediate code actually looks like for our example. It's basically our original idea broken down into super simple step-by-step instructions. And hey, look, remember that note the semantic analyzer made? It's now a real command right here, int to real 60. The beauty of this code is that it's generic. It doesn't care if you have an Intel chip or an ARM chip. It's a universal language for the inside of the compiler.
Okay, now for my favorite part, the optimizer. This is where the compiler gets really smart. It looks at that simple code and basically says, you know what, I can do this better. It notices we're turning 60 into a real number and then multiplying. Why not just do that all at once? It combines steps, gets rid of unnecessary temporary variables. It's all about getting the exact same result, but using way fewer, faster instructions. This is what makes your final program snappy.
And here we have it, the final product rolling off the assembly line. This is the target code. It's assembly language, custom-made for the specific computer processor it's meant for. You see these commands here? They're basically instructions like, hey, CPU, load this number into your R2 memory slot, and now multiply that by 60.0. This is pretty much the last stop before everything gets turned into the raw ones and zeros the machine truly understands.
But wait, this whole assembly line doesn't just run by itself. There are a couple of, let's call them supervisors, that are involved in every single step, from beginning to end, working tirelessly behind the scenes. If we look back at our factory map, you'll see what I mean. See how these two boxes are connected to everything? They're not just another station in the line. They're more like essential services that every other station relies on, all the time.
So who are these unsung heroes? First, you've got the symbol table. This is your factory's inventory manager. It's a big list that keeps track of every variable and function you've created, what it's called, what type of data it holds, everything. The other hero is the error handler. This is your quality control department. Anytime you mess up, a typo, a logical error, this is the system that catches it, gives you that helpful or maybe not so helpful error message, and decides if the problem is bad enough to shut down the whole factory line.
Okay, so we've taken the grand tour of the code factory. But you might be thinking, this is cool, but why do I, as a developer, actually need to know this, right? Why bother looking inside that black box?
Well, let's just quickly recap the whole wild ride. We started with our code. The front end tore it apart into tokens, checked its grammar with a syntax tree, and made sure it made sense. Then, the back end took that approved plan, turned it into a generic intermediate code, polished it up with the optimizer, and finally built the machine-specific assembly code. It's a pretty amazing process when you lay it all out.
And that gets to the why. When you understand this process, the magic disappears. You start to see how to write better, more efficient code because you have a sense of what that optimizer is going to do. Your debugging gets way smarter. And hey, if you ever want to design your own programming language, well, this is step one.
So there you have it. That's the incredible factory that turns our thoughts into software. This basic design has been the gold standard for decades. But it does make you wonder, right? With programming languages getting weirder and hardware getting crazier, what's next for the compiler? What new futuristic stations are we going to have to add to this assembly line? Something to think about.